Welcome. Today's assignment is 7th week assignment, that is mainly on nonlinearity and synchronization. Okay, let us see what are the assignment questions and corresponding answers. The first question: the third order intercept point of a nonlinear device is, there are 4 options: more than 1 dB compression point, less than 1 dB compression point, equal to 1 dB compression point, none of this. This is just a definition type of thing. Third order intercept point is more than, less than, or equal to, or with 1 dB compression point, what is the relation. So, let us look at the plot what we have seen in the class. This is power input versus power output. So, the fundamental component which has a slope 1 goes like this. As the input increases, the output also increases linearly, and at some point of time it starts getting saturated. That is, as we increase the input, output does not increase linearly. So, this point, when it is deviates from the virtual projected linear curve, it deviates by 1 dB, then that point is called 1 dB compression point, whether it is with respect to input or with respect to output. And the third order intercept is generated by third order component. Now, third order component generates much later because of its coefficient. So, it comes out of the noise level much later, but because it is cube, its slope is 3, it goes up very fast. But since it gets generated much later, if the projection of this third order component is linearly projected upward, it intersects the fundamental at some point, which is called third order intercept point. Third order component also will have a nonlinearity. Now, obviously, since this third order component generates much later, even if its slope is higher, this intercept point is much higher than 1 dB compression point. So, therefore, we can say with respect to output third order intercept point value is much larger than output of 1 dB compression point. In the question it was put reverse, 1 dB compression point is lower or higher. So, answer is A. The question was more than 1 dB compression point. So, third order intercept point is more than 1 dB compression point. So, answer is A. Let us see the next question. Two single tone frequencies 3718 megahertz and 3728 megahertz are input to power amplifier. I red colored this power amplifier because it could be SSPA type power amplifier or TWTA type of power amplifier. Both has some nonlinearity. So, it is operating in nonlinear mode. Operating point is such that it is operating in nonlinear mode. So, it will generate all sorts of intermodulation. Considering up to 5th order intermodulation effect, which of the following frequency will not have intermodulation interference? That means, once these two pure tones of two different frequency, which is 10 megahertz apart, if they generate the second order, third order, fourth order, fifth order intermodulation, then those intermodulation spurious will have different frequency. Now, here is a list of frequency on which is any one of them on which that intermode product will not fall. So, that interference will not be there. So, which one, where it will not fall? We have to consider up to 5th order intermodulation. So, let us see. Let us take one frequency as 3718, other one omega 2 is 3728, and try to calculate the intermode products, especially third order and 5th order, because second order and fourth order will be far away. So, third order, one of them is 2 omega 2 minus omega 1. If you put the values, you will come to 3738, and 3738 is C option. So, it is falling over that. So, C is ruled out. So, like that, if we do 2 omega 1 minus omega 2, you get 3708, that is also one of the options. So, that is also ruled out. 3 omega 1 minus 2 omega 2, this is one of the 5th order intermod, 3698. So, let us see. 3698 is also there in B. So, that is also ruled out. The last one is 3 omega 2 minus 2 omega 1, which is 3748, and let us see 3748 is not there here, and something like 3728 is there. So, on 3728, which is one of the fundamental, the intermod product is not falling. So, the answer is A. Let us see the third question. A deep space probe is moving away from Earth at a velocity of 15 km per second plus minus 3 meters per second. It is going away from the Earth. The probe transmits at a 14 gigahertz with transmitter clock drift of plus minus 10 to the power minus 9 hertz per day. Receiver at Earth has clock drift of 10 to the power minus 13 hertz per day. And after 30 days of silence, the probe starts transmitting to Earth. Now, that signal will be reaching to Earth, but since this is going with a velocity along with some variation in velocity. So, there will be some Doppler, and there is a stability of the transmitter, there is certain stability of the receiver clock. So, all of them will have some contribution, so that the frequency at which it is transmitting at 14 gigahertz, it may not reach exactly at 14 gigahertz. So, it will be slightly away. Now, how much big window we should open to catch that receive frequency? There are options given A, B, C, D, that is 1120 hertz, 560 hertz, 420 hertz, 140 hertz. So, let us see how do we do it. Three components are to be considered: Doppler shift of the transmit frequency, transmitter frequency instability accumulated over 30 days, because after 30 days it is transmitting, receiver frequency instability accumulated over 30 days. Each of the above component are plus minus, could be either positive or negative side change. So, worst case if we have to do, then resultant worst case frequency should be taken as 2 times the summation of all above 3 components, that will be our window. So, let us put the values. Doppler shift is calculated as 140 hertz, 14 gigahertz and 3 meters per second. Frequency shift due to transmitter instability over 30 days is 10 to the power minus 9 was the instability, plus minus 1 in 10 to the power minus 9, and 30 days 14 gigahertz. So, instability could be 420 hertz, and frequency shift due to receiver local oscillator, that instability is 10 to the power minus 9 minus 13. So, that comes out to be 0.042 hertz. Now, all these things in worst case they can be one sided. So, they have to be added, and then they could be plus or minus. So, plus and minus both sides together, it is 2 times of addition of this, which comes out to be 1120.084 hertz, and one of the option was 1120 hertz. So, the correct option is A. Let us see the next question. This is a longish question. A low noise amplifier and mixer are shown in the figure. This is a low noise amplifier and there is a mixer. The amplifier has a gain of 20 dB, that is G, and third order intercept point is of 22 dBm reference to the output. So, OIP3 dash 1 prime we have 22 dBm, and the mixer has a conversion loss of 6 dB. Instead of gain it says conversion loss, it is 6 dB, and third order intercept point 13 dBm reference to the input. So, IIP3 double prime, since it is second stage, is 13 dBm, but it is referenced at the input. If you remember, we said that whichever is higher, that is used by the industry as a reference point for third order intercept. So, in this case it is 13 dBm put as a input. Now, find the intercept point of the cascaded network for both phase coherent assumption and random phase, that is non-coherence assumption. So, it is a cascaded network, third order intercept point we have to calculate, and there are options given for both the coherence and non-coherence. There are options given A, B, C, D, different values are given. Let us see which value it matches. So, first what we have to do, this is reference to the input, which we will convert to the reference to the output, that is third order intercept point for mixer, and then we will do the calculation. So, reference of IP3 for the mixer from the input to its output we have to do, and the gain of the mixer G2 is negative of loss. G2 we can define as a negative of loss, that is in dB. So, OIP3 will be IIP3 double prime, OIP3 double prime, that is for the mixer, double prime for mixer, that is second stage, is IIP3 double prime minus G2, that comes out to be 7 dBm. Now, all values which are given in dBm for our calculation we should convert into ratio, that is milliwatt. So, OIP3 prime, that is for the first stage, the third order intercept point is 22 dBm, that is given, which comes out to be 158 milliwatt, that is for the first stage, that is the amplifier stage. And OIP3 double prime, which we have just now calculated, is 7 dBm, which corresponds to 5 milliwatt, that is for mixer. And the gain of the mixer G2 is negative of loss, that is 6 dB, which comes out to be 0.25, that is for the mixer. Now, we have OIP3 prime, OIP3 double prime and G2. So, for coherent case, the cascaded network third order intercept point is given by 1 by G2 into OIP3 prime plus 1 by OIP3 double prime and inverse of that. So, if you put the values, you get it 4.4 milliwatt, which correspond to 6.4 dBm. So, we got one of the answer, that is coherent case. In case of non-coherent, the expression is it will be 1 by G2 square into OIP3 prime square plus 1 by OIP3 double prime square and root over minus root of that. If you put the values, it comes out to be 4.96 milliwatt and 6.9 dBm correspond to values. Let us put the values again, that is for third order intercept point for cascaded network, coherent case is 6.4 dBm, non-coherent case is 6.9 dBm, and that comes out to be the choice B. So, right answer is B. Let us see the next one. Now, here it says a station is allotted to start its burst 1.5 millisecond from the start of reference frame having frame duration of 4 millisecond. This seems to be a TDMA problem, TDMA synchronization problem. To start the burst synchronization process with an estimated 1 hop propagation delay of 125 millisecond, find when the station transmits its burst from the start of the receive reference burst. A station has been allotted a burst transmission time away from 1.5 millisecond away from the reference burst time, that should be at the satellite. The frame duration and propagation delays are given. Now, since he is not sure when to transmit with respect to the reception of the reference burst, start of the reference burst, how far away, after how much time he should transmit, so that he meets this 1.5 millisecond criteria. And there are 4 options given: 1.5 millisecond, 2.5 millisecond, 3.5 millisecond and 4.5 millisecond. Let us see. Let us draw the picture first. In these type of cases, we draw the picture first. You recollect this picture shown in the class? This is in the satellite, this is time axis. In that the frames duration of f, many frames are shown, m times f, m is a number, integer number, m times f is shown. Let us say this beginning of this frame, it reaches after a propagation delay p n at the nth station. So, here he sees as a start of reference burst, start of reference frame. So, the receive station sees, actually it is on the satellite much earlier than by the propagation delay, one propagation delay. Now, he should transmit with respect to this after some time d. If he transmit, imagining that he is transmitting the reference burst, it should coincide with the actual transmission of reference burst at the satellite. He will not transmit, this is the estimation of time. With respect to that, he will transmit after t time, after t second, so that he reaches after t seconds at the satellite from reference burst. So, now if this is the number of frames, if you have a projection on the ground station, this m time f should be equal to d plus 2 into propagation one direction propagation delay 2 into p n, and then we can find out, since p n's are known and f is known, putting some value of m we can find out d. So, if you can find out d with respect to d, you transmit t second or millisecond later. So, d, the expression to find out d is m times f minus 2 p n. F is the frame time, p n is the propagation delay between the satellite and the earth station, nth earth station. We have to select this m such that d is less than 1 frame time, though diagrammatically it is not, it is shown much bigger, but it should be less than that. You should select m such that. Then burst transmit time with respect to reception of reference burst is d plus allotted time slot, that is T n, d plus t. So, you reach at the right allotted slot position. So, now we put the values. We know that d is equal to m f minus 2 into p n. Assuming m equal to 63, I have shown directly the number 63, you may have to iterate a little here and there. You will get 63 into 4, that is frame time, 2 into 125 millisecond, that is one side propagation delay, comes out to be 2 millisecond, and then d plus T n is 1.5 millisecond later it has to be transmitted. So, it is 3.5 millisecond, which comes out to be option C. Okay. Next, the third order intermodulation distortion is a measure of distortion created by DC signals, 2 carriers, single carrier, all of this. Let us see. The third order intermodulation effect is a measure of distortion created by in nonlinear devices. When 2 carriers of the same or different frequency are given input to the nonlinear device. With single carrier or with no carrier like DC, generation of third order distortion is not possible. So, the appropriate option is B. That is simple logic. Now, let us see another definition type of thing. The spurious free dynamic range is defined as the maximum output signal power for which the power of third order intermodulation product equal to noise level of the component divided by output noise level. The maximum output signal power for which the third order intermodulation product is equal to noise level divided by output noise level. The second option is maximum signal power for which the power of second order intermodulation product is equal to noise level of the component divided by. So, this is third order intermodulation product going to noise level. The B option is second order intermod product to noise level. Next option is the maximum output signal power for which power of the third order intermodulation product is equal to the noise level of the component divided by input noise level. This is almost like A, but there it was divided by output noise level, here it says input noise level. And last option is the maximum output signal power for which power of the second order intermodulation product is equal to the noise level divided by input noise level. B and D are almost same, except the division is by output noise level in one case, input noise level in another case. So, let us try to understand and then we will get it. We draw this picture again, input power, output power and this third order intercept point, and third order the component coming out of the noise level. That is when the signal power to the noise level ratio, that is what is spurious free dynamic range. You see, spurious free dynamic range third order when it is just coming out of the noise level. This is third order 2 omega 1 minus omega 2 or another third order, one of the fundamental, right. So, the arguments, let us see, the option B and D are ruled out because they are talking about second order intermod. It does not create distortion near the fundamental. So, spurious will not come in the fundamental. The option C considered input noise for output dynamic range, that is wrong. So, obviously, the option A considers output power and the third order intermod level and the output noise. So, option is the correct option is A, and diagrammatically also we have seen its correct option is A. So, the next question. Two sinusoidal signals with amplitude ratio of 2:1 are applied to a nonlinear component. Assuming Taylor series expansion, what is the relative power ratio maximum to minimum in dB of the resulting two third order intermodulation products? Their amplitude ratio is 2:1, that is one information, and we have to find out maximum to minimum third order what is the ratio, because it is unequal component. So, third order also will be unequal. The options given are 14, 16, 18, 22 different dB values. Let us see which one is correct. Calculation is very simple. You have to get the third order component. Let us assume the amplitudes of the two tones are, one of them is 2 V, another is V, 2:1. So, coefficient of two third order intermod will be 3/4 A3 2 V cube and 3/4 A3 V cube. So, the power ratio will be the square of these two, the larger one maximum to minimum, larger one is taken on the numerator. Since all other components will get cancelled, you will get a number 64, which is equal to 18 dB, and which meets the option C. Next question. A receiver noise figure of 14 dB, receiver has noise figure of 4 dB. A receiver has noise figure of 4 dB. 1 dB compression point and third order intercept point, both are reference to output. Now, it is both are output. So, we do not have to do any conversion. They are 15 dBm and 25 dBm respectively, 1 dB compression point and third order intercept point, and the receiver has a gain of 40 dB. If the receiver is fed with an antenna noise temperature of 150 K, find the minimum output back off required for spurious free operation. Assume T0 is 290 K, bandwidth is 1 megahertz, and for simplicity assume SNR is 0 dB. Now, 4 options are given: 11, 22, 30, 33, 44 different dB values. Let us see how do you calculate. Noise figure is given as 4 dB. So, equivalent noise temperature for the receiver is TE will come out to be at 290 degree K the receiver is. So, it comes out to be 438.44 K. Convert into then 150 K noise is coming from the antenna, that is at the input. So, equivalent noise temperature of the system itself is input plus this value, which comes out to be 588.4 K, which is in dBK, convert 27.70 dBK. Now, the corresponding noise power. So, overall noise power of the system is, in terms of dB, is G, that is gain, T what we have got, Boltzmann constant K, and the bandwidth B. Gain is 40 dB given, T we have calculated 27.7, K is minus 228.6, and bandwidth is 1 megahertz, which corresponds to 60 dB hertz. So, it comes out to be minus 100.9 dBW, convert into dBm, it comes out to be minus 70.9 dBm. Why convert to dBm? Because our 1 dB compression as well as third order intercept point are given in dBm. Now, linear dynamic range is 1 dB compression point to N0. So, subtraction of these two comes out to be 85.9 dB, that is linear dynamic range. And spurious free dynamic range is in dB, it is 2/3 of OIP3 minus N0 minus SNR minimum. In our case, given SNR is minimum is 0. So, SFDR is 2/3 of 25 minus the minus 70.9, which was noise. So, it comes out to be 64 dB. So, SFDR is 64 dB. Now, if you recollect the curve, that is from 1 dB compression point, that is almost saturation, and then we have to come to spurious free dynamic range. That much back off if we give, then we will not get any spurious. So, the difference of LDR, that is linear dynamic range, minus SFDR. So, required output will be 21.9 dB, subtraction of these two, and which is very near to 22 dB. One of the option was 22 dB. So, appropriate choice is B. Let us go to the next one. Again a very long question, that similar deep space probe. Let us see. A deep space probe is moving away from Earth at a velocity of 10 km per second plus minus 1.5 meters per second, same as the previous one. The probe transmits at 8 gigahertz, transmission frequency is different, 8 gigahertz with transmitter clock drift of less than plus minus 10 to the power minus 9 hertz per day, similar stability. Receiver at the Earth has clock drift of less than plus minus 10 to the power minus 10 hertz per day, it is slightly poorer. But the question is, after 45 days of silence, the probe starts transmitting towards the Earth. Determine the maximum time offset. Last time it was frequency band where it should fall, the actual frequency. Now it says how much time offset, after how much time. We know it is after 45 days is coming, but after that how much time is there in time offset. The time of arrival of the downlink transmission. So, this time part has to be calculated. Assume in the beginning the uncertainty of the time and frequency of the probe is 0. So, there are 4 options given 86.4 millisecond, 0.10648 second, that is 106 millisecond, 106.48 second and 68.4 millisecond. Different way it is written, but they are all different values. Now, let us see how do we proceed. Now, we have to calculate the time of offset. The time of arrival uncertainty is a combination of uncertainty in the probe's frequency. Probe's frequency is drifting. So, time calculation has to be as a cycle counting, and based on the probe frequency you will be doing that 45 days calculation. So, if the probe frequency drift, that calculation will go wrong, there is an offset here. Uncertainty due to range variation, because the velocity is changing. So, because of that the time will be delayed, arrival time, and initial uncertainty of the probe frequency. So, 3 things have to be given. Now, time uncertainty due to probe's frequency variation over 45 days, this expression we have studied in the class, it will be delta t square by 2 and 10 to the power minus 9 was the stability, 45 days. So, these many days it is shifted, and in a day 86,400 seconds. So, it comes out to be 0.0874 second, that is the time uncertainty because of probe frequency variation. Range uncertainty is the uncertainty at velocity. So, that comes out to be that 1.5 meters per second it was changing. So, for 45 days in terms of second, if you convert, it will be 0.01944 second, and initial time offset was 0. So, addition of this, substituting these values, we get 0.10684 second, which the appropriate option is B. So, with this we complete the assignment 7. Thank you.